Hello, persistent programmers, and welcome back to our 11th lesson on Circuit Python and the Circuit Playground Bluefruit. We're going to be covering plotting in Mu, and we're going to use the accelerometer, which can sense motion along 3 different axes. So, Mu has a plotter built into it. It can plot anything which is a tuple. Some call these tuples, tuples, same. Now, tuples in Python are sets of values in parentheses that have a comma or commas separating the values. Now you can have just one value in a tuple like this one that you see down here, which has in parentheses a 30 and a comma after it. And as long as there's a comma, we can go ahead and plot it when we simply print it out. The example at the right shows the Mu plotter with just one value. Here is a tuple with 2 values. You can see there's just a comma separating the 2 values. You don't have to have one on the end. And here's one with 3 values. Now the accelerometer on the CPB is a common accelerometer. It's actually called the LIS3DH. It's not a very friendly name, but if you happen to see this name in other code, it's referring to a standard low-cost, low-power accelerometer. There's one built right into the CPB. But you can see where the X points left and right, Y points front and back, and then Z is meant to be sort of through the ceiling and through the floor. That's your vertical axis. And this is how we set up our code. First, as we've done in other examples, we need to tell Python, hey, we need some libraries because we're going to be working with this accelerometer thing. And so we're going to import the libraries that you see here. Next, we need to set up our accelerometer in the same way that we've set up buttons or touchpads or pixel lights. And so that's this little chunk of code here. And the chunk of code, again, is not very friendly, but the good news is if you just copy and paste these 3 lines, just know every time you want to use the accelerometer, you have to include these 3 lines as well as the libraries that you have up here. And your accelerometer is going to be referred to as accelerometer. Now down here is what we're going to do in our while true loop. We're simply going to refer to the accelerometer that we set up here, and we're going to get the dot acceleration property. Now that's actually going to return the 3 values, x, y, and z. Once we have them, then we're going to put them inside of a tuple. Remember, that's inside of parentheses. And then by saying print, which needs another set of parentheses, so anything can be printed, and the tuple is going to be printed here, that will show not only it in the serial monitor, but it will also show it in the plotter. Now the time sleep just means wait 1/10 of a second. It gives us just a very slight pause in between each reading of the accelerometer so we can read things a little bit better. And if you wanted to read and have fewer plots, just feel free to make this number larger. So you might be wondering when you see things, what are these numbers? Well, acceleration is measured by this sensor in most accelerometers in meters per second squared. Now, you might have heard the term g-force. G-force is the Earth's gravitational pull at sea level, and that's about 9.3 meters per second squared. So if you take a look and you've got your Circuit Playground Bluefruit on its back, you should probably see on the z-axis something that's around 9-ish meters per second squared, and it's going to change even though the device isn't moving. There's always a little bit of variation that occurs even when things are flat. So this is what I want you to do. In your challenge, I want you to enter all of this code here and then figure out what happens to X, Y, and Z as you slowly move in each direction, left and right, up and down, and facing up or flipping over. So I'll pause here so you can update your code, and then we'll come back and try this out. So here's my code in Mu from where we left off in the previous lesson. And what we need to do is we need to import, we've already imported time, but we do need to import the Adafruit_LIS3DH module. We also need to import bus.io, and that's it for our imports. Now, why don't I, underneath this, set up my accelerometer? And the code I'm going to say there is I2C. And in fact, all of these things mean something, but at this stage, it doesn't really make a lot of sense for us to talk about the very specifics of what's happening with the I2C bus or how you can change different ranges in the accelerometer. So we'll just put these 3 pieces of code in and say, hey, you can use this anytime you need the accelerometer. I'll show you how you can consult the documentation in just a little bit. So this first line is I2C equals bus.io, all one word, all lowercase, dot I2C, all uppercase, open parentheses, lowercase board, dot capital accelerometer underscore capital SCL. So that accelerometer underscore SCL is all caps, comma, lowercase board, dot, and all caps, accelerometer underscore SDA, close parentheses. Let's return the next line is where we name our accelerometer, and we'll call it accelerometer, all in lowercase, which is a good name for an accelerometer. We'll say that that equals Adafruit_LIS3DH. Those are all in lowercase, and that's the name of the library we imported. And then right after that, dot, and in capital letters, LIS3DH underscore, and also all caps, I2C. then open parentheses, and then in lowercase I2C, comma, and then address, all lowercase, equals, and this is a 0x19, and then close parentheses. And again, these first two lines are pretty gnarly, but all we're doing is we're creating the accelerometer, and now when we refer to the name accelerometer, we can get the data that we need. This next line, we set the range of the accelerometer, so it's accelerometer.range equals, that's all lowercase, and then in lowercase, Adafruit underscore LIS3DH dot capital RANGE, that's all caps, underscore 8 underscore capital G. And that just sets the range. We can set the range from 2, 4, 8, or 16G. Most examples in demo code will be range underscore 8 underscore G. Once you've entered these lines here and you've done the appropriate import, you're ready to use the accelerometer. Now I'll scroll down to the while true loop. I've got a lot of extra code in here that I'm not using in this particular example, but I might want to use this in a bit, so there's no point in me deleting it. It's not going to be harmful if I've got that extra code in there. I am going to delete everything after my while true loop though, and after the indentation right after while true colon, I'm going to type in a comment, get accelerometer values, and print/plot. And on the next line, I'm going to get the acceleration property of the accelerometer, and that actually is going to deliver 3 values. So I'm going to say x, y, z. Those are 3 variables, and I'll say they equal accelerometer.acceleration, which are the 3 values that are going to be returned from the acceleration property in the accelerometer I set up. Then I'll press enter on a new line. I'll type in print, open and close parentheses. Inside that, I'll do another open and close parentheses because I'm going to put a tuple in there, and that's going to be x, y, z. Now that I've got it in a tuple, when I print it out, not only will it show up in the serial monitor output, but it will also show up in the plotter. Then on the next line, I'm going to type in time.sleep, open parentheses, 0.1, close parenthesis, which will just take a 1/10 of a second pause in between each accelerometer reading. Now let's go up here and click on save and see our results. If I click on serial, it starts to show me the 3 values that I printed out, and because I've set them in a tuple, notice they're in parentheses. If I go up here and select plotter, these are the 3 values that are being printed out. Now, the orange value that we're seeing here, this is actually the z-axis, and what you're seeing here is a reading of 1G that's showing up. So that's the gravitational force roughly at sea level where I am in Massachusetts, where I'm recording this, and there are 2 values that are showing up very close to 0. That's for the left and right and the front to back axis as well. But now, as you can see, I'm going to go over here with my CPB facing flat on the desktop, and I am going to lift my right side. Now notice as I lift my right side, the first number, which is the x-axis value, will increase as I move this vertically, and I'm about 9.8, roughly a G when I'm straight up. And now if I bring it back to the flat level, and then I lift it up again, this time on the left-hand side, I get a negative G, which is around -9, -10. Now if I take my CPB and lift it up so that the USB connector points to the ceiling, then I see that my Y value is roughly a G. If I go down and then put it in the opposite direction, facing straight down, then I get about a negative G, or roughly a -9 to 10. If it's flat on the desktop, we can see that the value of 1G is a little over 9 typically, but if I flip it over, then I get a -9. Now these values can help you recognize if something's being moved, but you can also detect a shake, because if you move it quite a bit, notice it shows some spikiness in there. That's because I'm moving more than the acceleration of the Earth's gravity when I shake things. So I'm accelerating it more than just the force of gravity, pushing it down in one way or another way. So hopefully that helps you understand acceleration in 3 different axes. Keep at it.